So let me recall that we have studied or discussed the continuous functions on some subsets, basically intervals on the real line, and we discussed what are the types of discontinuity, namely jump discontinuity or discontinuity of the first kind and the second kind. Then going to the derivatives, we defined what is meant by a derivative of a function at a point, and then we want to show something similar but in an opposite direction, namely we want to show that if a function is differentiable, then its derivative, the derivative cannot have any jump, derivative also cannot have any jump discontinuity. I am sorry about the monotonic functions, we have proved that monotonic functions all discontinuities are jump discontinuities, it cannot have discontinuity of the second type, whereas in case of derivatives it is the opposite. Okay, and in order to get to that result, we need some preparation. Of course, some of those things you already know, but still, for the sake of completeness, we shall recall. Okay, to begin with, let me recall the notion of what is called a local minimum. Okay, local minimum or similarly local maximum. Okay. As far as defining a local minimum or a maximum is concerned, we do not need, really speaking, any differentiability or any such continuity or any such condition, because that is just depends on the order structure of the real numbers. So this is something which we can define at in any set, or for that matter we can do so in any metric space. Okay, suppose X is a metric space, and f is a function from x to r, and we take x naught in x. Okay. Then we say that f has a local minimum at x naught. Okay, that is what we want to define. Okay, so f is said to have a local minimum remember, this term local is very important in this definition. Okay, you all know what is meant by a neighborhood of a point, right? That is something that is defined. Let me also mention here that there is a slight difference in the way in which neighborhood is defined in different books. If we take the definition of Rudin, it is any open set containing the point x naught is called a neighborhood of that point. Okay, whereas if you take Simmons, he says that any set which contains an open set containing x naught is called a neighborhood of that point. Okay, so that's a slight difference there, and so what Simmons will call open neighborhood is what neighborhood according to Rudin's. So, but in most of the applications that we consider about a neighborhood, we usually deal with open neighborhoods only. So we shall follow Rudin's notation. Okay, by neighborhood we will mean open neighborhood. That means an open set containing x naught, and in most cases it will be an open ball containing x naught or open ball with radius x naught. Okay, so so we will say that f is said to have a local minimum at x naught if there exists a neighborhood. Okay, suppose I call it neighborhood u of x naught such that what should happen is that in this neighborhood, for every x in this u, fx should be bigger than or equal to fx naught. Okay, then we say that f has a local minimum at x naught. Okay, so such that fx naught is less than or equal to fx for every x in u. Okay, is this clear? For defining this, we don't need any additional property of f. F has to be just defined, and it should be a real valued function. Now, a similar definition can be given for local maximum, right? A similar definition, is that clear? Similar definition can be given for a local maximum. So we'll just make it here, local maximum what will be changed here? Instead of this, suppose I want to say maximum, this inequality will be reversed, okay. Fx naught will be bigger than or equal to fx for every x in u. So let me simply say similar definition for local maximum. Okay. Now this is for any metric space. Next, what we want to observe is that if this is happening, in particular if x is a real line or some subset of a real line, okay, then, and suppose for example in particular if f is an interval, okay, and suppose f has a local minimum or local maximum at x naught, then, and if also if f is differentiable at that point x naught, then the derivative should be 0, okay. That is something you already know, but let us recall the proof, because that is something we shall need in proving proving the theorem which I mentioned in the beginning, okay. So by the way, let me also mention this minimum and maximum also sometimes together are referred as extreme values or extremas, alright. So let us now come to this observation or theorem, okay. Suppose f is defined from AB to R and f has a local minimum at x naught in the open interval AB, okay, x naught in the, if f is differentiable at x naught, then derivative at that f prime, derivative at that point x naught must be 0, alright, and similar statement for local maximum, okay. Okay. Now let us just see how we can prove this. So let us go to the proof of this. We can see these things little bit quickly, because most of these things you are already supposed to know. We are just revising because we need it in proving that theorem about the derivatives. Okay. Alright. So coming back to this, so since f has a local minimum at, let us take this case, f has a local minimum. F has a local minimum at x naught means there exists a neighborhood such that in that neighborhood this happens, okay, and in case of x naught, neighborhood means open set, and every open set will contain an open interval, okay, and we can call that interval as x naught minus r to x naught plus r for some positive r. So we can say that there exists r bigger than 0 such that for every x in x naught minus r to x naught plus r, what should happen? F of x naught should be less than or equal to fx, okay, f of x naught should be less than or equal to fx. Okay. Now suppose you take any h which is positive and less than r, suppose we take any h, okay. So consider 0 less than h less than r, and also consider f of x naught plus h minus f at x naught divided by h. Okay. Then what can we say about this? Since f of x naught is less than, see, once this h is less than r, x naught plus h lies in this interval, okay, x naught plus h lies in this interval. So we must have that f of x naught must be less than or equal to f of x naught plus h. That means this is a non-negative quantity. You are dividing it by again a non-negative quantity, right? So this must be bigger than or equal to 0, okay, right. And so since this is true for every h bigger than 0, and what we know is that the derivative is the limit, derivative is the limit of this as h goes to 0, okay, so this must be bigger than or equal to 0, okay. So this implies that we can limit of this f of x naught plus h minus f of x naught divided by h, and limit of this as h tends to 0, this must be bigger than or equal to 0, okay. Or which is same as saying that f prime at x naught is bigger than or equal to 0, okay, that is okay. Now in a similar way, see what we have done now is that we have taken h between 0 to r, similarly we can take h between minus r to 0, okay. That is, see when you take h from 0 to r, it means, see this is, let us say this is x naught, this is x naught plus r, and this is x naught minus r. When you take h between 0 to r, it means x naught plus h lies in this part, okay. So we can similarly consider minus r less than h less than 0, in which case it means that x naught plus h lies here, okay, x naught plus h lies here. But we can say that in, okay, let again consider this, so f of x naught plus h minus f x naught divided by h, okay. This time what is the argument? We can again say that the numerator is bigger than or equal to 0, but this time denominator is negative, okay. So this quotient will be less than or equal to 0, so this is less than or equal to 0 for all h. Then again you can follow the same steps as we have done here, so taking limit as h tends to 0, that will give that f prime at x naught is less than or equal to 0, okay. So we will say that f prime at x naught is less than or equal to 0, okay. And then combine these two things, we have shown that f prime at x naught is less than or equal to 0, and here we have shown that the same thing is bigger than or equal to 0. So combining these two things, we obtain that f prime at x naught is equal to 0, okay, that's clear, okay. Now in a similar way you can prove if it has a local maximum, right. Only thing is that these inequalities will be reversed, okay. Another way of seeing the same thing is that if f has a local maximum at x naught, then minus f has a local minimum at x naught, okay. And so the derivative of minus f at x naught is 0, which is basically same thing as saying that f prime at x naught is 0, okay. So whatever we do, the conclusion will be the same, okay. Now next thing that we will obtain from here are the various versions of this mean value theorems, okay. Now in case of mean value theorem, basically we use the fact that you have already discussed the properties of continuous functions on compact sets, okay. In particular, we know that if a continuous function on a compact set is always bounded and it attains its maximum or minimum value in a compact set, and every closed and bounded interval on the real line is compact. This is what we shall use in proving the next result, what is again well known, what is called Rolle's theorem. Again this is something you would have seen, but perhaps without realizing that you are using the compactness of the interval in getting the main idea of the proof, or getting the main thing in the proof. So let us say, what does Rolle's theorem say? That suppose we consider a function, suppose f from AB to R is continuous on this closed interval AB, and differentiable in open interval AB, then there exists a point C in the open interval AB. Okay, now one more thing. Okay, differentiable in AB and values of f at A is equal to f of B, and for the sake of convenience we can assume that value to be 0. Okay, f of A equal to f of B, though this part is strictly not necessary. Okay, though this, okay. Then there exists a number C in AB such that, okay, I have said already that I shall be using this short form such that, okay, such that f prime C is equal to 0. Okay. Now before going to the proof of this theorem, let us just see what this theorem says geometrically. Okay, that is, you have a function. Suppose we just look at the graph of the function. Suppose this is, okay, let me draw it there. Let us say this is A and that is B. The function is 0 here as well as here. Okay, so it may start either go up or go down, but whatever it is, ultimately it has to come down and meet this point B. Okay, so what this says is that at some point C, its tangent should be parallel to x-axis. Of course, it can happen at several points. Okay, it may happen at several points, but there should exist at least one point at which the slope of the tangent is f prime C is, as you know, f prime C represents the slope of the tangent. Slope of the tangent is 0 is same as saying that the tangent becomes parallel to x-axis. All right. Okay. Now, where does this all maximum, minimum, etc. come into picture in this? It is what I said just before starting this theorem. Okay, that f is a function which is continuous on AB. Okay, and AB closed interval A to B is a compact set. Okay, so the function must attain its maximum or minimum, some maximum as well as its minimum at some point in AB. Okay, right? Let us say at some point. Okay, that is the in fact beginning the proof. Okay, the function attains its maximum as well as minimum inside the interval AB. Okay, inside the interval AB. Okay, so suppose I call those points as x1 and x2. Okay, okay, so we can say that since f is continuous on the compact set AB, at some point it has to attain its minimum and at some point it has to attain its maximum. Okay, so we can say that I will call those points namely x1 and x2. We can say that there exists x1 and x2 in AB such that, suppose it is minimum here and maximum there. Okay, it is minimum here and maximum there such that f at x1 is less than or equal to f at x is less than or equal to f at x2 for every x in AB. Okay. That is, it is minimum at x1 and maximum at x2. Okay. Suppose one of these points is an interior point. Okay, let us take that as a, suppose one of the, let us say if x1 or x2 belong to AB. Okay, okay, let me first take the case x2 as well. Suppose x1 belongs to AB. Okay, okay, then it is an interior point. Okay, it is a minimum. Okay, In fact, if this happens for every x in AB and if it is an interior point, you can always find a open interval containing that point inside which this happens. So it is also a local minimum, it is also a local minimum. And since we have assumed that f is differentiable in the open interval AB, if x1 is in the open interval AB, f prime at x1 must be 0, okay. So you take C as x1, okay, right. So if x1 belongs to AB, then f prime x1 is 0, we take C as x1. Similar argument if x2 is in AB, okay. Similar argument if x2 is in AB, if x2 is in open interval, okay. We can say similarly if what is the argument here? Since x2 is a maximum, you can consider in fact this open interval AB to be its neighborhood, okay. So in that open neighborhood, it is f of x2 is bigger than or equal to fx, okay. So it's a maximum, and since f is differentiable at x2, f prime at x2 must be 0, and in which case you can take C is equal to x2, right. So what is left? If both of these things are not possible, in what way it can happen? Both x1 and x2 must be endpoints, okay. Both x1 and x2 must be endpoints. That is either x1 equal to A or x2 and x2 equal to B, okay, or x2 equal to A and x1 equal to B. In fact, argument in both cases is similar, okay. Let us just look at that, okay. So this is one case, okay? If one of the points is in interior, otherwise both x1, x2 are endpoints. So what is the possibility? That is, we can say case 1 is x1 equal to A and x2 equal to B. Of course, either case the proof will be the same, okay, and case 2 is x2 equal to A and x1 equal to B, okay, right. In either case, let us look at case 1. Suppose x1 equal to A and x2 equal to B. What do we know about f at A and f at B? Both of them are 0, okay. And now look at this, okay. Suppose x1 is A and x2 is B, this will mean that 0 less than or equal to fx less than or equal to 0 for all x. So this will mean that f is a constant function 0, okay. So this will, for example, this will imply that fx is equal to 0 for all x in AB, okay. That means it is a constant function, so its derivative is, wherever it is differentiable, its derivative is 0. So you can take C as any point in the interval, in the open interval, okay. And similarly in this case, even if x2 is A and x1 is B, still it will mean that fx is 0 for all x. So it is a constant function and its derivative is 0 everywhere. Wherever it is differentiable, its derivative is 0. So you can take again C as any point in the open interval. Is that clear? Okay. So that completes. Of course, I am sure you would have seen this theorem earlier and used it also, but perhaps you have not realized this step in the proof, okay, that the proof depends crucially on the compactness of the interval AB, okay. Now before proceeding further, let me just say something about notation, okay, and that is something which is used fairly often while discussing these mean value theorems, okay. We have said that C is a point in the open interval AB, okay. C is a point in the open interval AB, which is same as saying that A less than C less than B, okay. That is, if you draw the diagram AB, in fact it cannot be B or A, it has to be some point other than So if you look at this, what is customary is that look at this C minus A divided by B minus A, okay. C minus A divided by B, this is a number which is C minus A is strictly less than B minus A, so this is a number which is strictly less than 1, okay, and also strictly bigger than 0, okay, strictly bigger than 0, okay. It is fairly customary to call this number theta, okay. Theta is equal to C minus A, and suppose you call this as theta, okay, then you write this C as A plus theta times B minus A, okay, A plus theta times B minus A, okay. Or another way of writing the same thing is, this is same as saying that this is 1 minus theta times A plus theta times B, okay. And this last thing is what is called the convex combination of A and B, right? You may have come across this word, convex combination of A and B. So what we are saying is that if it is a point lying in the interval, okay, of course with this understanding we can even take C as A or B. If for example you take C as A, then you can take theta as 0, and if theta is 1, then C will coincide with B, okay. Alright, so this is something that is used commonly. Instead of saying that there exists C in AB, one says that there exists theta lying strictly between 0 and 1, such that f prime and that, okay, whatever you write this C in terms of theta, okay, A plus theta into B minus etc. is 0, alright. Then let us again go to the next theorem in this same spirit. It is called mean value theorem, and that is, it is called Lagrange's mean value theorem. What is the difference? We will have this, both of these assumptions. F is continuous on AB and differentiable in the open interval AB. Only thing is we skip this last assumption. We don't assume anything about the values of FA and FB, okay. So suppose F from AB to R is continuous in AB and differentiable in open interval AB. As I said, we are not assuming this last thing, but the conclusion is again similar. It says that there exists a point C in AB satisfying something, not this equation, something else, okay. Then there exists C in the open interval AB such that FB minus FA is equal to F prime C into B minus A, okay. Now before proceeding further with the proof of this theorem, let me first observe a few things, okay. Is it clear to all of you that this Rolle's theorem is a special case of mean value theorem, right? Because if you get mean value theorem, you can prove Rolle's theorem also, because suppose this is true, then in addition, if FA equal to FB, then this left hand side becomes 0, so there should be this F prime C must be 0, right? So one could have said that you just prove this mean value theorem and then get Rolle's theorem from that, okay. The only problem with that is that the standard proof of mean value theorem uses Rolle's theorem, okay. That is why we prove Rolle's theorem first, okay. And what is the proof? We construct a function which satisfies all the properties of this Rolle's theorem and get a point C, and then show that that point C satisfies whatever is written here, okay. All right. So that is the proof, okay. Now again, just as we have seen this geometric interpretation of Rolle's theorem, it is again convenient to look at the geometric interpretation of this theorem also before proceeding further. Now let me again go back to this graph here. Okay, one can write this equation in a slightly different form. Okay, I can say f prime c equal to whatever remaining here. Okay, so what does this mean? That here it will mean that f prime c is equal to fb minus fa divided by b minus a. Okay, f prime c is equal to fb minus fa divided by b minus a. Now we have already noted that f prime c represents the slope of the tangent at the point c. Okay, right, that is something we know. Okay, what about this fb minus fa divided by b minus a? What does that represent?
Secant line tangent.
Right, it represents the slope of the chord joining the point A. Of course, fa need not be 0. Fa can be somewhere. It can be somewhere here also. Okay, fa the point fa and AFA and BFB. Okay, let us suppose I change this graph here. Okay, let us say at A it may be somewhere here. Okay, it may be something like this also. Okay, this is B, then this is the point AFA and that is the point BFB. Okay, so the chord joining, slope of the chord joining these two points. So this is the point BFB, and this is the point AFA. So that number on the right hand side is the slope of the chord. Okay, and what does the theorem say? That there exists some point C in the interval such that the slope of the tangent is same as the slope of that chord. That means the tangent is parallel to that chord. Okay, the tangent is parallel to the chord joining the points A, F, A. That is okay. You can say in this case some maybe somewhere here. Okay, that can be C, or it can be also somewhere here. Okay, right. Remember, we have not said anything about uniqueness. Okay, even in Rolle's theorem or in Bean-Waller theorem, we have not said that the point C is unique. In fact, in this second case, when we said that the function can be constant, then in fact any point in the interval AB can be taken as the point C. Okay, so the point C given by the conclusion either by Rolle's theorem or Bean-Waller theorem is never unique. Okay. Okay. So what we do now is that we just consider the difference between the curve, this curve and this straight line. Okay. Okay, just consider the difference between this curve and that is the function which we call big F. Okay, that difference becomes 0 at the end, two endpoints. Okay, so at some interval its derivative should be 0 and that will give the required thing. Okay, that will give the required thing. Okay, so what will be the equation of this straight line, the point line straight line joining AFA and BFB? Suppose our arbitrary point here is, let us say, xy. Okay. Okay, for example, I can say that y minus a, no, y minus fa divided by x minus a, that should be same as, okay, one can say fp minus fa divided by x minus a, or which is same as saying that y is b minus a. Thank you. Okay, or which is same as saying that y is equal to fa plus x minus a, okay, into this fb minus fa divided by b minus a. Okay, all right. Now what I do is that consider define the function. Suppose I call that function big F from AB to R, big F from AB to R as follows, as big F at x is equal to fx minus fa minus x minus a into fb minus fa divided by b minus a. Okay. All right. So what does this big F represent geometrically? Okay. The first term is, say, the curve y equal to fx, that is the given curve fx here, okay, and the second term, that is this straight line, right, that is this straight line. So at any point it represents this. For example, suppose you take the point x here, it represents this difference, okay, it represents this difference at any point, right, okay. Now the idea is to show that this function big F satisfies all the hypotheses of Rolle's theorem and hence the conclusion, okay. So let us check one by one. Is big F continuous? See, what are, where can the problem, this is small f, that is continuous anyway, this is a constant function, x minus a is a continuous function, this is multiplied by a constant, okay, so that is continuous in AB, that is no problem. So f is continuous in AB. What is the next thing that we require? It is differentiable in AB, okay. So what about that? Look at the right hand side, we already know that small f is differentiable in AB. This is anyway constant, that is differentiable everywhere, okay, right. X minus a is again a polynomial, differentiable everywhere, and okay, you can say that this whole thing is a polynomial, okay, it's a this part is constant, right. So wherever small f is differentiable, big F is also differentiable, okay, because this is the only term which decides, okay. So and we know that small f is differentiable in the open interval AB, okay, and differentiable in the open interval AB. So we can say that hence that is it satisfies all the hypotheses of Rolle's theorem, hence by Rolle's theorem, yeah, we have to check that, okay, that's right, thank you. What about big F at A? It is small f at A, so this part is 0, A minus A, that is 0, okay, so fine. So big F at A is 0. What about big F at B? This part will be FB minus FA, then minus B minus A multiplied by this, okay, that B minus A should cancel with this, and what will get FB, so ultimately FB minus FA minus FB minus FA, okay. So this is also 0. In fact, you can go back to this diagram and see that we have observed that big F represents a difference between this curve and this straight line, okay, and that difference becomes 0 here as well as at this point here, okay, alright. So using Rolle's theorem, we must get a point C such that at that point this big F prime at C becomes 0, okay. So you can say that, so by Rolle's theorem, there exists C in the open interval AB such that big F prime at C equal to 0, okay. Now let us rewrite this. What is big F prime? We know what is big F at X. We know what is big F at X. So find out what is big. So differentiate this. So what we know is that F prime at X, that should be same as small f prime at X. Derivative of this is 0, okay, derivative of this is 0, and derivative of this x minus a will be 1, okay, and so this will remain as it. So f prime, big F prime at X is nothing but f prime at X minus this, fb minus fa divided by b minus a. Okay. So put it back here. So big f prime at c is equal to f prime at c minus this fb minus fa divided by b minus a. Okay, divided by, and we have shown that that is 0. That is 0. Okay, and that is same as saying that small f prime at c is same as fb minus fa divided by b minus a, which is again same as what we wanted here. Okay, fb minus fa is equal to f prime c multiplied by b minus a. Okay, that's clear. Now there are several uses of this mean value theorem, and many of those things you would have used without perhaps realizing that what is involved here is the mean value theorem. Let me just give one example. You know that if a function is monotonically increasing in an interval, okay, then its derivative, and if it is differentiable, then the derivative must be bigger than or equal to 0, right, and that simply follows from the definition, right. Okay, right, because suppose we look at the definition again, it is limit as h tends to 0 f of x plus h minus fx divided by h, and suppose you take some interval containing x. Okay, suppose you take some interval containing x, and if fx is increasing, then if h is positive, fx will be less than or equal to f of x plus h, that divided by h, so the whole thing is a positive, and so its limit will be bigger than or equal to 0. Okay, and similarly if h is negative, okay, if h is negative, this will be less than that, but this h is also negative, so the ratio will be still be positive. So taking the limit, you get that the derivative is bigger than or equal to 0. And similarly, one can show about the monotonically decreasing function that the derivative must be less than or equal to 0 at those points. Okay. And again, a special case of this is when the function is constant, the derivative must be 0. Okay. But let us ask about the converse. Okay. Suppose we know that the derivative is bigger than or equal to 0 in an interval. Okay. Can we get from that fact that the function is monotonically increasing in that interval? Of course, you have all used this. Okay, you have all used this, but you can realize that it does not follow from this definition. Okay, it does not, because from this definition you will only be able to show that it is f of x less than f of x plus h in some small interval containing x. Okay, but whether that happens throughout the given interval, that will not follow. Okay? That will not follow, and that will follow by using mean value theorem. That will follow by using mean value theorem. Okay, let us just see how. Let us again assume that f satisfies this same hypothesis. What is hypothesis? Okay, we can call this the corollary of the mean value theorem. Okay, suppose f satisfies the hypothesis of Lagrange's mean value theorem. In the interval a to b, that means it is continuous in the closed interval, differentiable in the open interval. Okay. And okay, the first thing that we want to say is that if f prime x is bigger than or equal to 0 for all x in AB, then f is monotonically increasing. increasing in AB. And similar statements about f prime less than or equal to 0, f prime equal to 0, etc. Okay. If f prime x is less than or equal to 0 for all x in AB, then f is monotonically decreasing okay, and if f prime x is 0, then it is monotonically decreasing as well as increasing, so it must be constant. Okay. Right. All right. Let us just discuss the proof of this using mean value theorem. This will follow in a similar way. Okay. Now, what is required to show that a function is monotonically increasing? Yeah. Right. You take 2 points. If x is x and y, if x is less than y, then f of x should be less than f of y. So let us consider the 2 points. Okay. Consider a less than or equal to x. Okay. Anyway, we want to show in the open interval only. So a less than x, a less than x, less than y, less than b. Okay. Now we have assumed that the function satisfies the hypothesis of Lagrange's mean value theorem throughout the interval a to b. Okay. So in particular, it does satisfy also in the interval x to y. Okay. So remember how we have taken x and y. This is, let us say, this is a, x is some point here, y is some point here, and that is b. Just consider this interval x to y. Okay. So suppose I apply mean value theorem to that interval x to y. By mean value theorem, there should exist some point between x and y such that fy minus fx should be equal to the derivative at that point multiplied by y minus x. Okay. So we can say that, I will simply say, by mean value theorem, and for this I prefer to use this notation here. Okay, because instead of saying it lies in the interval, again I have to use some more notation, the point z or some such thing, etc. Okay. So we will say that there exists theta by mean value theorem, there exists theta in the interval 0 to 1 such that fy minus fx is equal to f prime at x plus theta into y minus x, and this multiplied by y minus x. Okay. Now let us take this first case. We know that f prime x is bigger than or equal to 0 for every x in AB. So in particular, this is bigger than or equal to 0. Okay. And y minus x is also bigger than or equal to 0. So fy minus fx is bigger than or equal to 0. So we have proved that whenever x is less than y, fx is less than or equal to fy. That is the same as saying that f is monotonically increasing. Okay. In a similar way, you can prove for, in fact, up to this the argument will be the same, and at this point, instead of using this, you will be using this. Okay. Right. Okay. And of course, this is something that you would have used earlier also, without realizing that what is involved there is in mean value theorem. Okay. To convince yourself, you can try to prove this without using mean value theorem. Okay. And you will see that it is not possible. Okay. Right. But that you will not understand unless you make an effort to prove. Okay. So this is about the mean value theorem. Then what we want to do after this is, there is a more general form of mean value theorem, okay, which is called Cauchy's mean value theorem, and which deals with, instead of dealing with one function, it deals with two functions. Okay. But I think that is something we shall do in the next class. Okay. Today we'll stop with this.